Never be afraid. There's nothing which is known which can't be understood. And there's nothing which is understood which can't be explained. For over 50 episodes now, my team and I have brought you to the very frontier of knowledge in physics and astronomy. And still, our mission goes on. To present you with your birthright, an understanding of the universe. I've traveled the world seeking out a certain type of genius. Masters of not only their academic disciplines, but also at explaining their research in understandable ways. And I've bestowed upon these women and men the title of Titanium Physicist. You're listening to the Titanium Physicist podcast, and I'm Ben Tippett. And now, allez, physique! There's something universally appealing about a picture of stars. Now think about social media. Photos of stars are literally everywhere. It might just be selection bias talking, but anytime someone wants to write an inspirational quote to share on the internet, there's a respectable chance that they're going to put it over a star field. Anytime you want people to feel humility or awe or encourage a kid to study math, stars. Pictures of stars. Anytime you want to encourage people to think aspirationally, stars. Or Michael Jordan. I mean, some of the oldest images and charts drawn involve plotting the location of stars. It predates paper, even. And a lot of people might explain that these old maps of constellations are there for navigation or timekeeping or astrology. Sure, maybe, I don't know. But I'm willing to argue, just for the sake of argument, that a good deal of the motivation behind it is just that people like looking at stars. I mean, they like it even more if they can do it in the daytime, when it's warm, without hurting their necks. Incidentally, did you know that our eyes are not such bad instruments at gauging how bright a star is? And I'm couching my argument here because I don't want to give you the impression that we're robots, but I would have guessed that our eyes' ability to quantify how bright a star is would be somewhere between terrible and not worth trying. It seems unbelievable to me that you could use the human eye with all the subjective experience involved at looking at something and then trying to describe it and turn it into a number that has scientific value. But Hipparchus, an astronomer 2,000 years ago, came up with a numerical scale for describing how bright stars are, numbers between 1 and 6, where a really bright one is a 1, and a really barely visible star is a 6. And the numbers you get, judging by the eye, are actually pretty good and consistent. You can actually use these numbers to meaningfully describe the actual brightness that you would measure with a bona fide instrument. Modern astronomy has even inherited this numerical system of describing how bright things are. We call the number the magnitude. Anyway, mapping out the stars by hand is tiring, and no one can tell which dots are actual stars and which dots came from you sneezing on the paper. So stellar photography is the thing. You take a photograph of the stars, and then you don't have to do all that drawing. And photography is, in principle, an easy thing, even if you haven't invented it yet. You find a chemical that gets dark when you expose it to light, and then you smear it on a piece of glass or wood or something, and then you expose it to the image, and then parts of the light will turn dark, bada boom, bada bing. I mean, there's a lot of chemistry in finding the right chemicals and the right materials and in developing the image afterwards so you can look at it without the whole thing turning black and all that stuff, but this isn't a titanium chemistry podcast. So yeah, it's pretty straightforward. But even then, the history of stellar photography is absolutely bananas, and mostly because it was so hard to get everything right. Old-fashioned photographic techniques like daguerreotypes require that things stay still for a really long time. And stars are pretty dim, and they're always turning. Well, I mean, the Earth is turning, technically, but it just meant that it didn't work. It didn't work very well at all. And so it was around the 1870s and 1880s when the technology finally became advanced enough to photograph pictures of stars. And it wasn't just motivated by laziness either. In 1883, the amateur photographer Andrew Isley Common took the first photographs of stars too dim for the human eye to see. See, there's some cleverness here. Photography allows astronomers more sensitivity than the human eye. And furthermore, it provides you with a physical record of what you're looking at night, so you can study it. For instance, you might make your graduate student count the number of stars in a galaxy. Or you might take a photo of the same star once a year and then compare photos over the years to see if that star moves around. Astrophotography has become a wonderful research tool, and it's allowed us to better qualitatively and quantitatively study what stars are doing and what they're made of. But we don't do it using photographic plates anymore, just like we don't really take photographs using film anymore. And the reason is simple. We've developed light-sensitive imaging tools which are more responsive and practical than just using light-sensitive chemicals. But how do they work? I mean, how do we take light and turn it into electronic signals that can then be processed into a picture? It's a big question. Today on the Titanium Physicist podcast, we're talking about how our fancy digital light detectors work. Now, speaking of compelling images, I have decided that the very person for this topic would be one of my favorite authors. She writes in all genres of speculative fiction, from steampunk to science fiction, and she's won the John W. Campbell Award for Best New Writer, as well as more Hugo Awards than I can count. Welcome back to the show, Elizabeth Bear. Hello.
Hi, how are you?
I'm great. So, Bear, for you today, I built a brand new team, 2 experts in building detectors. Arise, Dr. Suresh Sivanandam.
Beep boop.
Dr. Suresh is an astronomer who did his undergraduate degree with me at UBC and then a PhD from the University of Arizona. He's currently an assistant professor at the University of Toronto, where he works at the Dunlap Institute and is an expert in the design and construction of imagers and spectrographs. Now arise, Dr. Danica Marsden. Dr. Danica is an astronomer who did her undergraduate degree with me at UBC and then a PhD from the University of Pennsylvania. Afterwards, she was a postdoc at UC Santa Barbara, where she did research on MKID detectors, and she's currently a project manager working for D-Wave Systems. All right, everybody, let's talk about how technology works.
It's elves. It's all elves.
Little elves turning
Little
cranks.
elves. Yes. Yes, like the little people inside your television.
It kind of is magic, actually.
Well, that's why actors have to be so much thinner now, because television screens have gotten much skinnier.
So let's start by talking about telescopes specifically. The imaging technology that we're going to be talking about today, we're going to talk about different types of light detectors that we use to take in light and turn it into electronic signals somehow. And all of these have applications beyond just telescopes, but telescopes are a good way to talk about it because they're pretty much just that, right? I mean, if you want to talk about the one in your cell phone, then you have to be like, well, okay, what about usability and mode? No, we just want a thing where you shine an image in it, take a picture. Simplify the discussion just a little bit, okay? Even though things like CCDs, for instance, get used in all sorts of applications nowadays, not just the Hubble Space Telescope.
Yeah, so in fact, I mean, it's nice to think of the history of CCDs, which became the first real mass-produced image sensor.
Okay, now what's a CCD? What does that stand for?
Charge-coupled device.
Thank you.
Isn't that descriptive?
No.
Yeah.
I know, right? For the first time ever.
What a useless piece of information.
Euphemism stands for.
Well, no, but once you hear Suresh's explanation, then it will all be clear.
It's true. It's true.
So there was research going on in Bell Labs where they were trying to design new forms of computer memory, and then they discovered that, it was actually sensitive to light. And then they did a little bit more research related to that, and they actually came up with this new device that could actually record images electronically. And it was called a charge-coupled device, which sounds very esoteric, of course. And the reason it's called a charge-coupled device is the way this particular sensor reads out. So it's got lots of pixels arranged in a grid. So when the light hits this device, it generates electrons. So every photon of light that hits the device, it can generate an electron. And then it's stored in the pixel. And then the way they get the electrons out of the pixels is they basically shift the charge from pixel to pixel. until it gets out on the other end of the sensor where you have a little amplifier that reads it out. And that's why it's called charge-coupled device, because each pixel is coupled and you shift the charge across it.
Mm-hmm. Like a fire bucket brigade.
Yes, that's the perfect analogy for it.
And how it creates the electron is that each of those pixels is a teeny tiny little slab of silicon with little atoms of germanium or some other element in there. And so when the photon comes in and hits the germanium atom, it knocks an electron off,
thereby creating a free-roaming electron.
Thereby creating a free-roaming electron. Okay.
Okay. So the idea here is you have this plate of silicon. You want a way to record where the light is hitting it. And so you specially make this crystal so that it has the type of atomic properties when a photon comes in, if it has enough energy, it will knock free one of these electrons. And then you'll get kind of a free-roaming electron where the photon hit the plate.
And then you want to trap that electron, otherwise it might roam away.
Yeah, I mean,
and then you won't know where it belongs.
Yeah, so how do you turn this plate covered in distributions of electrons into an image? How do you figure out where on this plate the electrons are free? And so that's what Suresh is saying. They use electromagnetic fields to trap the electrons into little squares, pixels, little regions. So you partition up the whole plate into little pixels, and then all of the electrons that got knocked free in any pixel will just kind of stay inside that pixel. And then we collect them all later.
And from the concentration of electrons, you can tell how many photons hit that area of the plate. Okay.
Yeah,
right.
exactly.
So if the first square has 3 electrons and the second has 0 and the third has 10, and then that tells you how many photons hit those pixels.
I'm kind of a ringer. I took 4 semesters of darkroom photography back in high school, back when it was actual darkroom photography. And this is not too different from how a silver plate works, except you're using crystals of silver and reading the result with your eye instead of using electromagnetic fields.
Yes and no.
Okay.
This is the cool part. So the principle is the same. In your film photography, light comes in, it causes a chemical change in that little pixel, right? And in this case, light comes in, knocks an electron free in that little pixel, and then there's a free wandering electron. So essentially, the exposure is the same. You take your sheet, you expose it to the light, you close your camera shutter, just like in regular photography, and then you have a distribution, in this case, of electrons over the things. And then we need to parse that into electronic signals. And like Danica said, we're going to kind of count up the electrons in each square. But how do we do that? This is the coolest thing. Okay, so the idea here is that every pixel it's like an electromagnetic well. So what they have is, on the side of every pixel, there are these 3 electrodes, okay? There's one on the top, one in the middle, one on the bottom. They're metal electrodes. We can use batteries, say, to change the amount of charge on them, change the electric field through them. So we can make the middle electrode really, really positive, and then the up and down ones really, really negative. And then the electrons, the free roaming electrons, will say, hey, I want to hang out by that big positive one in the middle because electrons are negatively charged. So we can use these electrodes to partition up the sheet into these pixels. These electrodes are what produce the electromagnetic wells that trap each of these collections of electrons. Okay, so then what they do is, once the sheet has been exposed, they start shifting around the electric fields generated by the electrodes so that all these wells of electrons start shifting up the sheet. And there's collecting amplifiers along the top of the sheet, and so it just kind of pushes them up off the top of the sheet in order. So there's only one row of collectors, and we're shoving all of the electrons through the collectors at the top. And so the order that these collectors receive the signals dictates how far down the sheet the electron wells started. Does that kind of make sense?
I think so. Are you talking about like the what would be, like scan lines on an old 300 baud modem kind of?
Yeah. I guess in the modems they do it. There's a dot that scans around, right? And in this case, each detector at the top tabulates one column at a time. So all of the electrons in one column end up going through the same one at top. So you're doing it line by line instead of one point shifting back and forth. But similar to that, yeah.
Okay.
One point I wanted to make is the reason these things are so great is compared to film, they're about 100 times more sensitive. These days, the sensors that you can get are almost 100% effective at detecting individual photons of light.
That's pretty magical.
Yeah, we're pretty much at the limits of physics now. We can't do much better than that.
I beg to differ, but yes, okay.
Oh, man.
Hey, fight!
Well,
No, don't fight yet,
I'm just saying in terms of detecting a photon. So we're very close to the limits of... I mean, you can't detect more than one photon for every photon.
Before we go on, do you guys want to hear a crazy analogy I came up with for how these things work?
Go ahead.
So, you ever been in an airport where there's like a big glass partition down the length of the hallway, where it's like American boarding gates on one side and Canadian boarding gates on the other, and you're not allowed to cross this wall because you need a
and the
passport?
restaurant that I want to go eat at is on the other side of the wall.
Yeah, you know exactly what I'm talking
Always.
about.
Yeah.
Imagine we've got that scenario where there's this big terminal, and imagine that a bunch of airplanes have all landed all at the same time, and these airplanes are full of little kids. So one airplane has like 5 kids on it, one airplane has 15, whatever. And so we want all of these kids to move down out through the end of the terminal where they can be collected, counted, that kind of stuff. But we want to keep track of which kids came off which airplane. So we don't want to mix them up. And for some reason, because they're still on American soil or whatever, we're not allowed to cross that barrier. So we're stuck on one side of this barrier. We're stuck on the glass side. All the kids are on the other side. So what do? We set up adults. You set up a row of adults running down the length of the wall. And each adult will have 2 things, a handful of broccoli in one hand and a teddy bear in the other. And we know that children love teddy bears and they hate broccoli, right? So what you're going to do is outside each terminal, you're going to have one adult holding a bear, and then the adults on either side of them are going to hold broccoli, right? And what this is going to do is the kids come off their plane and they don't know where to go. So they pile up on the glass near the bear and they don't go anywhere near the broccoli, right? So then you get these parcels of children along the glass wall, right? And then what you do is you have the adults switch hands in a really coordinated way. So closer to the end, you have one person with the broccoli change their hand and show the bear, and the kids shift down to the right, and then that person with the bear holds up the broccoli and shuts off all the kids, and you can shunt all the children down through the exit in order that they arrived on their airplanes without mixing them up and without interfering with them directly.
That's a pretty great analogy.
Yeah, that's very elaborate. Well, you will have a problem if one of those kids likes broccoli.
Well, we know that that's impossible.
So getting back to what Suresh was talking about, whether or not you see the kid in the first place, I believe that's known as quantum efficiency. Is that what you're referring to, Suresh?
Yes, that's right.
Okay, because you can lose kids sometimes.
Well, that's an ongoing problem, especially when the Airbus shows up full of unattended children and sort of dumps them in the going to America exile section of, say, Pearson Airport, where there's nothing but a terrible bagel place.
So I can stretch this analogy a little bit more. There is this thing called charge transfer inefficiency in CCD. So when you shift the electrons from one pixel to the next, there's a small probability that you'll lose some of those electrons. So I guess to stretch your analogy, there's always a small probability that 1 or 2 kids decided to stay on the aircraft because it was just much more interesting.
Mm-hmm. Or they swapped positions in the lineup or something.
Or they're running around on the tarmac. I think CCDs are pretty well explained at this point in time. Do you want to rattle off some trivia about what kind of awesome telescopes use CCDs? I guess everything.
Pretty much any astronomical telescope that's looking in wavelengths that we can see or close to is
with our eyes.
With our eyes are using CCDs. So the largest telescopes in the world, like the Keck telescope in Hawaii.
Gemini telescopes. There's one in Chile and one in Hawaii.
Right. And including the Hubble Space Telescope uses these devices.
And Kepler, the planet finder,
has many of these devices. Kepler has just got this very giant CCD consisting of something like tens of these detectors that are very, very efficient at detecting light. So one of the other characteristics of these things is very stable and well behaved. So if you're trying to look for a planet that's orbiting a star, tens of hundreds of light years away, you need to find minuscule changes in the brightness of the star as the planet transits in front of the star. Thanks to these devices, how stable they are, you can actually see an Earth-like planet orbiting around a star hundreds of light years away.
So the majority of the known extrasolar planets have been found with telescopes using CCD arrays.
So here's one question. You mentioned that we use this for light that we can see, optical light. What about, infrared?
That's a pretty loaded question, because infrared is very broad. There's near infrared, there's mid infrared, there's far infrared, and it all depends which part of the infrared spectrum you're looking at. And I'm guessing you're going to ask near infrared, which is where I do a lot of my work.
That sounds good.
So near infrared is, for example, our eyes are sensitive to a wavelength range of about 400 nanometers, which is blue. The sun's about yellow-green, which is around 550 nanometers. And then the edge of what we can see is about 650, 700 nanometers, which is red. And then CCD detectors are made out of silicon. And so silicon is actually sensitive to about 1,000 nanometers or 1 micron. That's the very near infrared. And actually, in a lot of cameras, they actually put a special filter, SLR cameras, called an infrared blocking filter, so that the sensor inside won't see light past red. You can actually take that out and actually see some of the near infrared. So in astronomy, a lot of work right now is being done in the near infrared, which is around the range of 1,000 nanometers to 5,000 nanometers. And that's because a lot of objects in the night sky emit their light at those wavelengths, and especially very distant galaxies, which are moving away from us very fast. Unfortunately, silicon-based CCDs don't work for looking at this range of wavelengths. And so there needed to be a new technology that can address this. And so you need to make a whole different kind of material that is sensitive to infrared light. And the current material that's very good is made out of 3 metals: mercury, cadmium, and tellurium. And in short, it's called mercad tellurite. So it's a weird alloy, and it's sensitive to these wavelengths of light. Now, the other problem is the physical process of how you detect infrared light is the same as we described for the CCDs, where the photon comes in, hits one of these atoms, and then ejects an electron that we then try to save and measure. So the technology used for this is what's called a CMOS sensor, complementary metal oxide semiconductor. So what these devices are basically every little pixel has a little amplifier. So it's called an active pixel. Unlike the CCD, where you have to push all the charge to the very end of the device and then amplify it, now you can amplify each individual pixel. And in the case of infrared detectors, you have this mercad telluride layer, which is actually detecting the light, but then you need the electronics, the amplifiers and readout electronics, which, given our current technology, can only be made in silicon. And so what you do is you build millions of these little amplifiers for each pixel, and then you sandwich and electrically connect the mercad telluride layer, which detects the infrared light. And then you get out your signals from that process.
So I was going to ask, just as a brief aside, what sort of things in the sky are more easily seen?
Oh, there's so many things. So the most exciting thing, I would think, for a lot of people is exoplanets. One of the big things going on right now in terms of developing new instruments for astronomical research is developing these cameras that can actually image exoplanets orbiting around nearby stars. And this is all done in the infrared.
Right. And what about brown dwarfs?
Yes, they are capable of seeing brown dwarfs. So the exoplanets they're trying to take pictures of are basically scaled-down versions of brown dwarfs. So they emit most of their light in the infrared.
All right. So, Bear.
Yeah.
Let's talk shop here. Essentially, the idea here is there's this whole spectrum of light, right?
Right.
And different objects will emit electromagnetic waves depending on a few different things. But one of the things that determines it is how hot they are, right?
Right.
I mean, if fire is red, it's hot. If the fire is blue, it's really, really, really hot, right?
Yes.
There's a temperature dependence on this. And so what they're talking about right now is they're saying there are things in the universe that aren't stars. Stars they're white hot or red hot. They're kind of visual hot.
Or blue hot.
Blue hot, yeah.
Blue hot.
But people also emit infrared radiation, things that aren't as hot as a star, but can still be pretty hot. Maybe it's hot because it's a planet near a star. Mm-hmm. You know, the planet has a temperature because the nearby star is kind of cooking it, and so it's radiating at a less than stellar hot, but still pretty hot temperature.
Right.
Maybe it is a great big object that's, a brown dwarf is a...
It's a star that didn't quite turn on.
It's a fizzled star.
Yeah, so it's hot like ashes, but not hot like a star. So the idea is if we can look into these parts of the electromagnetic spectrum, these features will become more apparent to us. They'll really pop out. There's a few things here. Suresh was saying that essentially silicon's transparent to these wavelengths. So our CCDs, you shine it at it, and it just goes through. It doesn't catch any of the light. It doesn't cause the electrons to pop off. Nothing happens. So the idea is that these CMOS detectors, they're made with a material that will absorb that spectrum of light and will kick off an electron that we can then measure. Does that make sense?
Yep, absolutely.
And sometimes, different types of detectors or wavelengths are complementary. Just as, you approach a foreign object and you look at it, try to understand what it is, but you might also poke and prod it and sniff it and maybe taste it. And in that way, sometimes using a bunch of different types of detectors that can see all of the different parts of the spectrum that this object might be emitting or absorbing the light from, you can learn about it.
So what percentage of the electromagnetic spectrum do we have the technology to detect with these various types of detectors?
Everything.
Excellent.
No, that's not quite true, actually. There are still large swaths of the spectrum that we don't have detectors that work very well.
Yeah, where's your Planck length photon detector, Suresh?
Okay, maybe, we have gamma ray observatories, we have had X-ray observatories, ultraviolet observatories, optical, that's passé.
Nobody
infrared.
cares about eyes anymore.
No, I think we got, as long as you go into space, you can cover most of the electromagnetic spectrum.
Enough that we don't really care about the remaining bits until something new comes along to convince us otherwise.
Right.
That's another interesting point they make. As Suresh just said, once you go into space, the deal is that the atmosphere... global warming. Let's talk about that. How does it work? There's gases in our atmosphere that interact very strongly with infrared radiation.
Yeah, so that's bad for astronomers.
Yeah. So the atmosphere isn't transparent at a lot of these different frequencies. It's transparent in the visual, which is why when we can look out and see the sun and the stars and all the fancy things, and deer that are a kilometer away. You can see pretty far in visual. Radio, it's transparent, but most of the things in between, the atmosphere will scatter the light. And so it's kind of like, I don't know, imagine it looking really foggy. The light signals stop being sharp. They get really blurred, splayed out. And so we can't use infrared detectors, usually, from ground-based observatories because the atmosphere is radiating in that spectrum and it will outshine the stars that we're trying to look at. It's kind of like being in the city on a really bright night where there's lots of light pollution and you can't see the stars. Yeah, so you can't usually see the stars in the infrared from the ground because the atmosphere is outshining the brightness of the stars.
Well, the nice thing is we have actually found little windows in the infrared where there isn't an atmospheric molecule that's absorbing all of the light. So a lot of astronomy is done in these small windows where we can actually look through the atmosphere.
Mm-hmm. But it is no coincidence that the window that is let through our atmosphere coincides with the wavelengths that our eyes can see.
Okay. Now you say that's no coincidence. Obviously, our eyes would evolve to, say we lived on Titan or someplace with a different atmosphere.
Mm-hmm. We would likely have evolved to be able to see...
Right. We'd have evolved a different...
other parts of the spectrum. Mm-hmm.
Yes.
So Danica mentioned something earlier that's absolutely fantastic. She mentioned that it's helpful when we're doing these things to look at different colors. Because, you look at an object in one color and compare to what you see in another color, and it gives you more information about what might be going on inside that star, say. based on our description, both CMOSs, CCDs, and even like black and white photography, they don't really care. I mean, there's a threshold, a frequency, but past that red light, blue light, it's all going to cause an electron to register, right?
Mm-hmm. Right.
So one question we might ask is, how do we use, say, a CCD telescope to see in color? How do we use a black and white plate photography telescope to see in color?
Well, there are many ways of doing it. So the crudest way is you use a filter that lets only certain color of light go through onto your sensor. And so you basically throw away all of the light that's not let through, and so then you get the color information by using different filters, and you take an image with a filter at a given time. So actually our cameras have filters in them too. The image sensors they have this thing called a Bayer pattern, where they have a red, green, and blue filter put on individual pixels. And then later on, when you take the image, it interpolates the color information from the different pixels and gives you the overall color of the image. The other way you do it is you build a spectrograph, and the spectrograph has a prism or some sort of element that spreads the light as a function of the frequency, and then you take a picture of that.
So it spreads the light into its rainbow constituents, and then you detect that spread out light with your CCDs.
So is that a clear bear? So you're like, I want to know if this traffic light is a red, green, blue, what? And so you take multiple photographs of it with different filters in front of them and then compare them. And you're like, well, this one has all red light because when I put on the green filter, it disappeared completely.
Well, I want to know where you're finding the blue traffic lights. Sorry, under the bus, Ben.
You did throw me under the bus.
I
For
did.
a speculative fiction author, you should be taking the hints I'm giving you and running with them.
Basically, what you're describing is identical to some tricks that one would use in old-fashioned film photography, or the reverse of that is how four-color process printing works.
Mm-hmm.
You have a yellow, a red, and a blue, and black ink, and you layer them over one another to get the full spectrum of colors.
Yeah.
So you're doing that in reverse. You're subtracting colors.
Right.
And that's why you always run out of cyan instead
Always.
of all the others. Right. So Suresh has informed us very nicely about what I would classify as the bread and butter detectors of, and nowadays the bleeding edge is making use of another revolution in materials science and condensed matter physics, which is to use superconductors. Superconductors are metals that, when you cool them down very cold to almost absolute zero, essentially all of the resistance goes away. So now we're experimenting with detectors made out of these materials. And I worked on what are called MKIDs, or microwave kinetic inductance detectors. What they do is, rather than these poor little photons that are traveling, billions of light years to get to you, and then you just chuck them in the garbage, because it's not the red one and it's not the green one. Instead, we make pixels of these MKIDs where every single little photon gets detected, and each pixel can tell what that photon's energy was without any filtering. So how do we do that? There's similarly this underlying sea of silicon doped with something like phosphorus, or you could use sapphire. We're still experimenting with the materials. This is cutting edge stuff, and we're still optimizing, but then you can lay down a circuit of this superconducting metal. It could be titanium nitride, it could be tungsten, and you make a little resonant LC circuit. So you have an inductor and a capacitor together, and it resonates at some particular frequency, which you specify by design, how you design the inductor and the capacitor. And then when a photon comes in and it's focused using a lens array onto the inductor, when it hits the inductor metal, this superconductor, it blasts apart a bunch of pairs of electrons that are known as Cooper pairs, which exist in superconductors. And all the Cooper pairs being blasted apart changes the inductance of the inductor, and then what you see as your signal is the resonance will shift the whole circuit's resonant frequency to one side, and the amount is proportional to the energy of the incoming photon. Does that make sense?
And the energy of the photon is...
That's the color.
That is the color. Okay, so it's the wavelength.
Yeah. Right. So if it's a red photon, it shifts this resonant frequency a little bit. And if it's green, it shifts it a bit more. And if it's blue, it shifts it a lot.
So yeah, it's a system that responds not just to the intensity of the light, but also its frequency. But I bet we can explain all the other stuff in there, because it's fantastic. Okay, so she just said something called an LC circuit. Have you ever heard of one of these before?
Nope.
Okay, that's fine. L stands for inductor, and C stands for capacitor. Okay, so it has to do with kind of geometry and charges moving through a wire. Okay? The idea is this superconductor that they have, it is in essence just a really complicated wire. The way it's laid out on this chip is really, really complicated, but in essence, it's a wire. And there are electrons that are moving around through this. So there's two things to keep in mind here. There's the capacitor and the inductor. And together they have a certain effect called a resonant frequency. And we'll talk about that in a second. So the idea here is that, okay, usually when we teach electromagnetism to kids in high school, we imagine that the response to the circuit is at the speed of light, but it's not.
I think the current of water in a river is a very good analogy to the current of electrons flowing along the wire.
Yeah, exactly. Because it takes time and stuff can build up and slosh around. And essentially what we're talking about here is the electrons end up sloshing around in this system.
At some point in their life, everybody should get doped up on cold medication and have somebody explain electrical engineering to them. There are no words small enough for me at this point.
So here's the thing. A piece of wire is neutrally charged, right? There's the same number of protons as electrons in it, right?
Right.
And so if you drive all of the electrons to one end will be negative, and the place they left behind will be positive, right? And positive and negative things attract each other, right?
Yes.
So what you can do is you can bend the wire into kind of a U shape so that if you drive all of the electrons to one side and that leaves positive charges on the other, the two ends of the wire that are almost touching really close together, those will feel each other pulling across a gap. The positive and the negative ends will interact with each other in a way called the capacitance.
Okay.
And so it'll kind of stick. Electrons hate each other, so they don't want to hang out together, but they'll be like, oh man, we're really close to a whole bunch of positive charge. We kind of like being on this end, only a little bit. Mm-hmm. And the other thing is something called inductance. It has to do with magnetic fields. If you have charges moving in a spiral shape, it will generate a magnetic field through it. And so there are these things called inductors, which it's an electronic component shaped like kind of a spiral. And what happens is, if you drive a current through it, it will generate a magnetic field, but that takes a little bit of effort. And so this object will resist changes in the magnetic field. It will resist changes in the current. So it'll be like, I like how much current we have right now. I don't want to change it. And so what happens in the system is you're hooking up a wire, a capacitor. The two ends are really close together with one of these inductors, a spirally shape, and then you're driving all the electrons to one end. And what happens is the electrons all go to one end and they go, we don't like being really, really close together. We kind of do, but not much. We're going to spread back out. And so they spread out, and that becomes a current moving down the wire. And then the inductor goes, hey, you're not allowed to change.
I've been in that relationship.
What you end up with is the electrons end up sloshing back and forth through the circuit. It's kind of like when you're like a kid, or you're in like the bathtub and you start kicking back and forth with that wave, pumping it, making it bigger and bigger.
That's the best explanation I've heard for a resonant circuit.
So there's a timing involved here. Depending on the geometry of the system, it will take more or less time for the electrons to cycle back and forth through the system, and so forth. Moral of the story is these things are determined by the geometry of the system. Okay?
Okay.
Yep. So for a whole array of these things, you can design them such that they're all slightly different, and therefore they all have a slightly different resonant frequency. And then you can read them all out at the exact same time.
Okay, so the idea here is that I can figure out what the resonance frequency of one of these LC circuits is by interacting with the electromagnetic field it generates. Pretty much the magnetic field, right? I said that coil is going to generate a magnetic field. So what you can do is you can take another external magnetic field and you can switch it back and forth at a certain frequency. And if you tune it just right so that the driving frequency matches the resonating frequency, then you're going to see the oscillations inside the circuit. The response is going to be huge. Like the system's just going to resonate. It'll sing like a wine glass when you sing its harmonic frequency, right? So what they're looking for is that singing back effect when they... Okay, so in this case, the system is made out of superconducting wire. And that's difficult to make, but superconducting wire has a really useful property, which is that the reason it's superconducting is that the electrons inside of it are all paired up. Boy, I mean, we've done whole episodes on superconductivity.
Yes.
What do you want to know more about how superconductivity works?
Sure, why not?
Oh, it's the cough syrup talking. Okay, so have you ever heard of the Pauli exclusion principle?
I don't think so.
Well, I'm sure you've talked in like high school chemistry about how an atom has electrons in shells, right?
Yes.
And all of the electrons aren't all in the lowest energy state shell. Instead, they're kind of stacked out, right?
Right. Yes.
And the reason for that is called the Pauli exclusion principle. No two electrons can share the same orbital shell. And this particular property applies to a type of particle called a fermion. Fermions have 1/2 spin. But there's another type of particle called a boson. And bosons have integer spin of 1, spin of 2. Don't worry about that. But the moral of the story is, if you cool down a material cold enough, all of the electrons will couple up together. And each individual electron is a fermion. But when they're interacting in this way, they effectively become a couple, and that couple acts as a boson. And so this bosonic state is what allows superconductivity to happen. So what happens when your photon comes in and interacts with your detector, in this case, is the photon comes in and it breaks up some of the electrons. And so they stop being coupled up, and so the system stops being superconducting in a few places.
Right, electrons are like siblings who are like, get away from me. And the Cooper pairs, these paired electrons, act like a romantic couple who want to occupy the same place.
So the moral of the story is your once superconducting wire now has all sorts of patches in it where it's not superconducting, and that changes the inductance. It changes the timing of the resonant frequency. And so if the system's just been hit with a photon, it's going to ring at a different frequency, and we can detect that change in resonant frequency. And that's what we're detecting. And that's how we can detect when one of these has been hit by a photon and its response. How its resonant frequency has changed in response to it depends on what color the light was. And so we can use exactly how much its resonant frequency has changed to figure out what color of light hit it.
Exactly.
So these detectors are bananas. Yeah, I didn't believe it when I saw it. So what you have is a whole array of these little wiry, spirally superconductor things, and each one will have its own resonant frequency. And so you can use them to detect not just light hitting it, but also what color it was. And you can do it without having to throw away all of the photons that you would just by using filters.
Fascinating.
They're very efficient with all of these little photons, and you can really wring a lot of information out of what's coming from the sky.
Well, one thing you want to know about astronomers is we are absolutely greedy about collecting photons.
They want
as many as we can get, we want to get. So if there's any way of doing that, we want to do it. Because every photon is precious.
So the last type of detector that we are going to talk about is a transition edge sensing bolometer, so TES bolometer. And this pertains to a very different part of the frequency spectrum. It's over in the radio part of the spectrum, and we wanted to see wavelengths about 1 millimeter long. And the reason is that 2 Russians back in the 80s predicted that we would see a particular effect. Their names were the Sunyaev and Zeldovich. So the effect is called the Sunyaev-Zeldovich effect. If you look out in the universe, the very furthest, oldest thing that we can see is the cosmic microwave background. And essentially, this is just the afterglow of the Big Bang. And this light peaks in the microwaves, which is why it's called the cosmic microwave background, and it travels 14 roughly billion light years all the way to us. And on its travels, it passes through and around all the intervening things that have formed over the life of the universe, such as galaxies, clusters of galaxies, and so on. And as it passes through a cluster of galaxies, the hot gas in the middle of this cluster of galaxies will actually absorb some of those photons. And so what happens is that when we make a map of this background light, we, at particular frequencies, will see what look like holes where these clusters of galaxies have essentially swallowed up those photons. And what's really cool about this is that normally when we want to try and see something out there in the universe, we have to collect its photons. But in this case, we're doing the opposite. We're looking at the absence of photons. And because it doesn't matter how bright it is, we can see these objects as far out as they exist. So it took a while for us to develop detectors that could see this radiation. It took a few decades to get it right. And we finally came up with an idea, which was to, again, we're using superconductors. So you take an absorber, could be silicon doped with phosphorus, for example, pixel, and you couple it to a superconducting circuit. And in the case of the Atacama Cosmology Telescope that I worked on, which is in Chile, there's another one in Antarctica called the South Pole Telescope that uses the same effect. So you could take a molybdenum gold resistor, which is a superconductor, and when a photon hits the bath, it heats it up. And the reason they're called transition edge sensing bolometers is that you set them on the transition between their superconducting cold state and their normal higher temperature state when they're warm. And so you set them on this sort of knife edge between those two states, and they're very sensitive to temperature changes. So the resistance of this circuit, the molybdenum gold circuit, changes a lot. When the photon comes in, it heats up this absorber, and the whole thing shifts off of its transition. And that is the detection of those photons.
So one photon is enough to cause this transition.
So as with the CCDs, right, you sit there and you integrate for a while and you look at one patch and you let the signal build up.
Okay, so this is a bolometer, which means it measures temperature. It's taking advantage of physics on a much simpler scale than all of the other detectors that we've talked about, but it's absolutely very, very clever. And the idea here is, okay, let's say we got a photon. It's really difficult to make one of these really, really fancy machines that absorbs just that photon and reads all sorts of information about it. But it's a little bit less difficult to just have something that absorbs the photon and gets warm. Mm-hmm. And so the idea is, what we do is we make a system that's really, really, really sensitive to temperature change. Now, superconductors, we talked about how there are these Cooper pairs that couple up. That effect is a real sudden thing. It's like a high school dance where there's all these, all these teenagers don't want to dance with each other. They're just hanging around, milling around, bobbing their head to the music, and you're like, no, I want them to couple up. And they won't. They won't. So you turn the temperature down. And what happens is there's a special temperature when the gymnasium is just cold enough that they're like, it's too cold, and they'll grab their date, right? And couple up. So it's a really, really, really sudden transition between the two. In fact, the transition between superconducting and non-superconducting is something that people studied for years and specify that it's one really special type of transition. So it's a really, really sensitive transition. So what they do is they tune their machine so that there are superconducting elements that are each superconducting element is embedded in a material that will absorb the heat from some photons, and they tune its temperature so it's just on the edge of superconducting. So right now it's superconducting, but if it gets any warmer, all those teenagers will split up and it will stop superconducting. And so each of these blocks that the superconducting material is embedded in, you expose it to light, it heats up just a little bit, and then the ones that heat up, those stop being superconducting. And you can measure the degree to which they're not superconducting and figure out how much the temperature has changed and deduce from that how many photons hit it.
So this is not something that measures Asiatic bears. That would be a bolometer.
Bolometer.
Yes.
I see.
Oh.
Yes, I said it too fast and my nose is stuffed up. It was nearly a joke.
And it's not a machine that measures intake of cereal in children either. That would be a bolometer.
Oh.
When we were talking about the Atacama Cosmology Telescope, which I spent some time operating in Chile, it always sort of puzzled people when they would ask me, okay, so when you go down to your telescope in Chile and you look through it, what do you see? And I'd say nothing. You can't look through it.
Yeah.
And even if you could, your eyes wouldn't see anything because they don't see these wavelengths. It always seemed very disappointing to people, but in fact, it even gets worse. So you take this data, you make your electronic picture or whatever, and you combine it using your computer. But for us, it could take weeks before you saw the picture on the other end. So, definitely no selfies, instant selfie where you can take the picture and go, oh, no, I need to fix my hair and then take again.
No instant gratification here.
Well, that was really fun. Good work, everybody. You pleased me. Your efforts have borne fruit, and that fruit is sweet. Here is some fruit. Thank you, Danica. That was wonderful. Here is a mango. Suresh, you get a durian. All right.
Just don't hit me with it.
I'd like to thank our guest, author Elizabeth Bear. Thank you for coming on the show.
Yay!
Would you like to tell your audience about your most recent books?
I do not actually have a book in 2016 because I had 2 books out last year. The first one is a Wild West steampunk adventure novel starring heroic saloon girls versus disaster capitalists.
Makes sense.
If you imagine like Leverage with hookers, that's basically it in the Wild West with gigantic sewing machines that you can drive like tanks.
Nice.
That's called Karen Memory. And the other one is a book called An Apprentice to Elves, which I wrote with Sarah Monette, which is a high mud Norse companion animal fantasy. Imagine like the Pern books meet Game of Thrones. Telepathic wolves and Vikings. What more could you want from life?
Right. All right. Well, that's it. Hi, everybody. Well, that was fun. Let's get to some announcements. First, again, please give us a review on iTunes, because that's where all the rankings of the podcasts go. Or you could tell other people about us online with your various online communities, with your Facebook and such. You could follow us on Facebook, incidentally, if you want. Follow us on Twitter. On another note, we are still humbly soliciting your donations. Your donations go towards paying server fees and also to our ambitious project to get all of the episodes transcribed. You can send one-time donations through our PayPal off our website, or you can go to our sweet Patreon site and give a recurring $2 donation. This particular episode of The Titanium Physicist has been sponsored by a collection of generous people. I'd like to thank the generosity of Mr. Patrick Nidenston and Mr. Jordan Young for their donations. I'd also like to thank Doug B., Ms. Julia, Mr. Noah Robertson, Ian, and Stu, Mr. Frank Philip from Austria, and Noisy Mime, Mr. Shlomo Dalal, Melissa Burke, Yassine Ouarzazi, Spider Rogue, Insanity Orbits, Robin Johnson, Madame Sandra Johnson, Mr. Jacob Wick, Mr. John Keys, Mr. Victor C., Ryan Kloss, Peter Clipsham, Mr. Robert Halpin, Elizabetha Teresa, Paul Carr, Mr. Ryan Newell, Mr. Adam K., Thomas Shire, Mr. Jacob S., a gentleman named Brent Evans, a lady named Jill, a gentleman named Greg, thanks Steve, Mr. James Clausen, Mr. Devin North, a gentleman named Scott, Ed Lowlington, Kelly Wienersmith, Jocelyn Reed, Mr. S. Hatcher, Mr. Rob Abrazado, and Mr. Robert Stietka. So that's it for Titanium Physicists this time. Remember that if you like listening to scientists talk about science in their own words, there are lots of other lovely shows on the Bracula Media Network. The intro song to our show is by Ted Leo and the Pharmacists, and the end song is by John Vanderslice. Good day, my friends, and until next time, remember to keep science in your hearts.
Angela, don't be mad. There's something I gotta tell you, dear, before before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet. Jumped through a window out into the haze. Hop down Magnolia Boulevard.